So welcome back, everybody, and welcome to this session, which will have its main focus on the HHL algorithm for solving linear algebra problems. So I'm going to step you through some of the basic elements, and what we are going to focus on is essentially the basics of the HHL algorithm, basic math and codes with examples, in particular on how to solve differential equations. And before that, we need to do a quick reminder about the quantum phase estimation algorithm, which we discussed last week and the week before, because that enters as an important ingredient in the HHL algorithm. If we get time, we will start discussing the quantum approximation optimization algorithm, which is another example of a variational quantum circuit. And this will also be the topic next week. So next week, we will have a full discussion of this algorithm. And after that, we will begin with machine learning methods like quantum support vector machines and quantum neural networks, which will be the last topics this semester. Then the Jupyter Notebook, which is a little bit different from the slides, is here, but I've also included the codes in the slides. Now, a quick warning, the slides contain a lot of information this week, but the essential part about the HHL algorithm is just contained in some 30 slides, and we will also go through them on the whiteboard. Now, at the end, after we've gone through the algorithm for the HHL algorithm, or the basic mathematics, there's a lot of material which links the HHL algorithm with the quantum many-body physics. So you can view that material as a kind of overview of specific applications of the HHL and parallels of the HHL with many-body physics. In particular, I'm showing you a kind of link between spectral methods, Green's function theories, and also time-dependent mean field theories like time-dependent Hartree-Fock theory and time-dependent density functional theory, because there are some parallels here. Now, the emphasis on the applications today is one, to solve a simple linear algebra problem, and you will be surprised by the simplicity of the problem. It's going to be a 2x2 matrix, which we can solve by hand, actually. And then we are going to look at how we can solve Poisson's equation with this algorithm. Now, but before we begin with the HHL, we need to remind ourselves about the QPE. So the next 10 slides is something which I will just go through quickly, because this is material which we also discussed last week. So last week, one of the things we did was actually to set up the unitary operator. And we went through the basic mathematics on why you get this specific expression. And the goal of the quantum phase estimation is to actually estimate this phase phi. And we can then link that phase phi with the eigenvalues of a given operator. Now, the reason why we use this now, or remind ourselves about the QPE, is because the QPE enters the HHL algorithm. So if you're thinking of project number 2, and you would like to use the HHL algorithm, what you would need as technicalities is a quantum Fourier transform and the quantum phase estimation algorithm, which we discussed last week. So this is yet another option for those of you who are interested in this specific path, okay? So the QP extracts the eigenvalue of U in phase form. Then, as we mentioned last time, it's a central algorithm in many physical applications, energy estimation in many body physics, Hamiltonian simulations. Hjorth's algorithm is very important, and obviously the HHL algorithm, which we will discuss in more detail today. So what we discussed last time was that the QPE uses 2 registers, one which is called a control register, and then we have a system register so that we can actually decouple the two and find the phases which then link with the eigenvalues of psi from the control register. So the control register is the one which stores the estimated phase bits. So what we did, the first step, was to create a uniform superposition. And you will see that in many of the applications which we end up doing. You will see that in particular when we start discussing quantum machine learning methods, that we are going to have what we call a parameterized quantum circuits. And the first thing we do with all the qubits is to perform a linear superposition. So these qubits are not entangled, but they are now in a linear superposition by a Hadamard gate. So that means that the total state, which you can see here, and we are using this kind of sloppy physics notation. So this is the initial state. So all the qubits are initialized to 0 in the control register. And this is just the tensor product. And we have just skipped the tensor product notation here. So that prepares the control register as a coherent superposition of all binary numbers k. Now, then we applied a set of control powers of unitary operations, controlled unitaries, and each control qubit determines whether the corresponding power is applied. So psi is an eigenstate, so that means that this psi here is an eigenstate of this operator, and we can actually write it out in terms of the phase phi, and each control unitary writes phase information into the control register. So if the control register base is k, then the operations give a new state, which looks like this. So this is your standard operation, which you also see in the quantum Fourier transform. So the combined state, and the states actually, due to the unitary control operations here, what you end up with is now a new state, which then contains this phase. It has the original qubits, which are actually there's a superposition of states, n times the tensor product with the psi here. So the system register factors out, and the control register now contains the phase information. That's the important thing. So the control register is in this specific state, which is a Fourier type state. And that's why the Fourier transform is so important. And that's why the the quantum Fourier transform is the next step. It converts this phase encoded information into a computational basis approximation of phi. So you apply the inverse quantum Fourier transform, and you have the codes for doing that from the examples from last week. And when you have that one, then you can extract this information phi, which is then given by the number of bits divided by 2 to the power of n, which is a number of possible configurations. And this becomes the state n, which is then encoded in terms of these bits. So the control register stores the exact n-bit binary expansion of phi. Normally, you won't have an exact representation of a number with a given finite number of bits. So typically, this example here shows a 3-qubit control register and the system register here. So you have the Hadamards, you have a controlled U operation. So this actually entangles the given qubits with the system. Then you can actually separate it out. So the state which you end up with is a state which looks like this, where you have separated the phases into the control register, which contains the phase information. And then you perform an inverse QFT, and then you perform a measurement on all the qubits. So when you have n control qubits, what the QPE resolves phases to an approximated value. So this would be the standard deviation, which goes like 1 over 2 to the power of n. So clearly, the more qubits you have, the better the precision. So if you have the 2 qubits, as we discussed last time, you can only represent the values 0. If you have 1 qubit, you can represent the value 0 and 0.5. If you have 2 qubits, you can represent 0, 1/4, 1/2, and 3 divided by 4. So the more qubits you have, the smaller the error, because you have a better representation of a binary float. So this exponential precision is typically one of the main reasons why QPE has been so powerful. When you look at the eigenenergies, so you would typically have a Hamiltonian, which has an eigenstate E, and an eigenenergy E as well, by using the same labels. Then, since H is not a unitary operator, it is assumed to be Hermitian, then you could rewrite everything in terms of a time evolution operator, which then is a unitary. And then you would simply have U of T acting on E. And that means that you would have U with, if you compare with this expression here, you can then identify the energies in terms of T and divided by 2 pi. So if you can implement this unitary operation here, then you can actually find the eigenvalues of a given Hamiltonian. And this is something which is then exemplified in the example from last week. So this is a quick summary. So the implementation of the QPE, you have choose the number of control qubits, you initialize the system register in a state, in an eigenstate, approximate eigenstate. So this is actually quite important because if you have, and we discussed that last time, if you have performed a VQE calculation like you did in project 1, then you have an estimate for the ground state. And it doesn't need to be perfect because you could say, let me use the VQE to get an approximation. So that means that you would have the state psi you're interested in, which then could be initialized as an approximate eigenstate. Alternatively, if you don't know anything, you would just approximate it with a set of bits, which are perhaps you should actually entangle them. So you apply the Hadamard's to the control register. You apply these controlled rotations. You apply the inverse QFT, and then you measure the control register. And then you interpret the measurement as an estimate of this phase. Now, the problem with the QPE is often that if you look here, if you have many bits, this becomes a pretty long circuit. And in the kind of noisy intermediate state quantum phase, which we are in now, where you have decoherence, you have noise in the circuits, then typically the QPE would need many, many qubits, especially if you want to apply it to Shor's algorithm. So an efficient implementation of Shor's algorithm, for instance, means that you have thousands of logical qubits. So basically, the Hamiltonian, you transform it to a unitary operation, you perform the QPE, and you extract the energy. So you can think of the quantum Fourier transform as the phase decoding engine inside the QPE. And VQE and QPE are complementary because VQE is a near variational energy estimator, QPE is a long-term high precision eigenvalue estimator, and the VQE can provide input states for the QPE. Now, what we are interested in now is another algorithm. And this algorithm here is actually a very nice implementation of quantum algorithms because it allows you to solve the linear algebra problem, which you will find, for instance, in solution differential equations. The inverse of that one is a typical problem you will find if in many Hamiltonian many-body physics problems. You will find it in machine learning. If you think of a standard linear regression, you actually in the need of inverting a matrix. So if you think of the mean squared error and you look at a linear regression, the basic old-fashioned, simplest possible, lowest level machine learning, you actually end up having to invert a matrix A. So this is the basic of the starting point. The core idea is actually to solve that linear system. So I'm going to step you through the basic elements. So in the slides here, as I said, there is much more material than what we will cover, but there is a lot of material which links this equation here with many of the many-body methods some of you have encountered when you took a course on many-body physics. So the case we are going to look at is actually the case where we have a partial differential equation. And the classic example you will encounter in all textbooks in quantum computing is Poisson's equation. And my lectures are no exception. I'm going to show you that one. And there is a code there which actually solves Poisson's equation with classical methods. So typically, if you think of that problem, A times an unknown vector X equal to a known vector B, you could set that up as a matrix inversion problem. So A is a matrix. Now, if you do this as a matrix inversion problem, that is normally inefficient, because the cost then, if the matrix A has dimensionality n times n, then the cost in number of floating point operations, if the matrix is dense, is n cubed. So that's expensive. Now, the case we are going to look at, Poisson's equation, is an equation which is going to reduce that matrix into a 3-diagonal matrix. Then there are efficient algorithms, and one of them is called Thomas algorithm, where you can actually solve that problem with n floating point operations. So you reduce the cost, the classical cost, by 2 orders of magnitude. And what you're going to see is that our fancy quantum algorithm cannot beat that classical algorithm for the simpler cases, okay? So let's say there are cases where you're looking after quantum supremacy. When we look at Poisson's equation, this is something which you can solve to high precision, really high precision, with classical methods, because the matrix is simple and the matrix is not dense. Actually, one of the features of the matrix which favors the HHL algorithm is a matrix which is sparse. So we are going to link this later with machine learning as well, and quantum machine learning, and also many-body physics. But the main focus in the lecture will be on solving a partial differential equation. In our case, Poisson's equation. So we want to encode the vector, and I'm going to switch over to the whiteboard pretty soon so that we can set up the basic elements. But I just want to give you the overarching idea. So B is now going to be the quantum state, and we are going to express that in terms of a basis. And we are going to find X as the inverse of this matrix times this vector B. And the output is a quantum state, not a classical vector. And we are going now to look at how we can simulate this and what are the basic mathematics. So I'm going to skip some of the slides here. The type of example which we will look at is the Poisson equation, as I said, but we will also link it to things like linear response theory here. So there's a phase estimation step, which we have discussed already, so I will skip that one. And this is the phase estimation circuit, which we repeated now. And I'm going to skip this one, but I'm going to simply say that there's a kind of notation which I will use now, which is a little bit more compact. So when we had the Hadamard gates and we apply the control powers, then when we perform an inverse QFT, we're actually getting the state back, which is this phi, which encodes the phase. So this is just a compact notation for us performing an inverse QFT, which finds the state phi tilde. And then we want to solve this problem here. So let's just try to look at a little bit at the mathematics here and go through this step by step now, okay? And you will find much of the same details here actually. But let's switch to the whiteboard so we can slow down the pace a little bit. So what we want, so the classical problem, which we mentioned, is that of a matrix A multiplied with a vector X equal to a vector B. We are going to use this to solve partial differential equations, but we will also link this with quantum machine learning. We are going to look at how this links with many-body physics. We are going to make some basic assumptions about the matrices which we have and the vectors. Basic assumptions. So we are going to have a dimensionality which is given by the number of bits or qubits. So this is the number of qubits. And we know that since these take binary values, then the total number of arrangements we can make is 2 to the power of n. We are going to assume that this matrix A is a complex matrix which has dimensionality n times n. The vectors B and X are obviously vectors, so they have dimensionality or length n. So we want now to find X so that X is a solution of AX equal to B, and that means that X can then be written as A inverse multiplied with B. So I'm going to come back to the typical problem, which you can solve here. So a typical problem is a partial differential equation. And I'm going to come back to the details there. But now I just wanted to set up the basic algorithm for the HHL algorithm. And again, one of the things which we are going to need now, so we mentioned the QPE, we have the quantum Fourier transform. So these are the basic kitchen items, okay, which we need to implement this algorithm. So A is also assumed to be a matrix which is Hermitian. So that's a basic assumption we are going to make, is Hermitian. If it's sparse, even better. It doesn't need to be sparse, but if it is, then this simplifies many things. So we're not going to put a constraint that it should be sparse, but sparse matrices often make life much easier. And we are going to assume that it is Hermitian and non-singular. So that means that the inverse exists. So that means that the inverse A minus exists. Keep in mind that we are not assuming that it is unitary, okay? That's a very important assumption. Now, one thing which we know then is that we can make the spectral decomposition. So if we now take the spectral decomposition, we know that a matrix which is Hermitian and which is non-singular, that means that there are many equivalent statements in linear algebra. So if the matrix is non-singular, that means obviously the determinant is non-zero. Eigenvalues are non-zero. It's invertible. So these are all equivalent statements when it comes to properties of a matrix. So since the matrix is non-singular, it means that we can find the eigenvalues, and then we can use the spectral decomposition. So we can actually set up, and this is one very important element. So if you spool back or reboot your memories to what we said before the Easter break, then we mentioned that the spectral decomposition plays an important role in many of these algorithms. So the spectral decomposition, which we discussed in the very beginning of the semester, says now that since we have made these assumptions about the matrix, is that this matrix A can then be written out in terms of the eigenvalues multiplied with the eigenbasis. And this is just a matrix. So that's the spectral decomposition of a matrix. Now, since we now have an eigenbasis, which we may not know, but we assume that the matrix is non-singular, then it means that we can now also expand this vector B in this basis J. And you see that one of the problems which we face is actually the problem of encoding the information in the vector B. So this vector B could represent actually some classical numbers, which you have to encode in a quantum state. But let's just look at the basic mathematics here. So that means that then this vector X is a vector which is going to be proportional to A minus 1 times B. And this quantity here is actually going to be equal. And I'm going to show you why this is the case. So this is going to be equal to J multiplied with Bj divided by lambda J and multiplied with U of j. So the essential part is that lambda j can actually give us an inverse of lambda j here. So A is not unitary. So keep that in mind. And that's why we will need the phase estimation algorithm. Because when we perform a unitary transformation, since A is not unitary, it means that here, let me just mention this as an aside. Here, we are going to need to look at E of A times T. This is a unitary object. So why does it look like this? So we said that this emission, we can make this decomposition. So these components, which we have here, let's put that one as another aside. These components beta j are obviously given by the overlap between uj and b. Okay. So let's show that this is actually the case. So formally, what we have is the following. So formally, we have A minus 1 is equal to J and Bj of lambda j times Uj. And you may ask, why is this correct? Well, it's correct because if we use the spectral decomposition, we have that this is given by lambda j multiplied with Uj and Uj. And that means, and you can easily show that, so I'm just going to state it, this simply means that the inverse of that matrix in the spectral decomposition is 1 divided by lambda j and Uj and Uj. And we know that when we take the matrix A minus 1 times A, this has to be equal to the identity matrix. Okay? So this is an important aspect. And in our case now, if you take and multiply this matrix here, A, in the spectral decomposition with the matrix A, you will quickly see that due to the orthogonality, so you need to keep in mind that these states are orthogonal. So when you look at the inner products, this is simply delta ij. Okay? And when you multiply these twos, what you're going to get is simply the completeness relation of uj, which is then simply the identity matrix. So this is an important aspect. So then what we end up with here, when we have shown this, when we now calculate A minus 1 times B, this is the same as J of 1 over lambda J of Uj, and this is then multiplied with K of beta J of U of K. And we know that these two states, this inner product, gives us a Kronecker delta. So this becomes simply the sum over Bj of lambda j of Uj. And now you see these kind of basic elements which we need. We need to find the eigenvalues of A, and that's where the quantum phase estimation comes into play. When we have the eigenvalues, then we can find the inverse. So what I'm going to step you through now are the basic algorithms which are needed in order to set up the HHL algorithm. So the algorithm itself, the HHL algo, it uses 3 logical registers. So one is the system register, which is then encoded initially. So we need to encode that one initially in B. That's the initial state which it is in, because remember now that we have a linear algebra problem where the vector B is known. And there is a phase register which is initialized in terms of a given number of qubits, all set to 0, initially in a state, which we write like all states in qubit 0. And then there's a tensor product for m qubits, okay? So this is a kind of standard notation which we have seen many, many times. Then there is an ancilla qubit, and it's on this qubit which we are going to make the measurement. So if you think of the quantum phase estimation algorithm, you will also see that that control register is called the register which contains the ancilla qubits. So that's a kind of name which you will encounter in the literature, an ancilla qubit. And if you look back at what we did with the QPE, we're actually making the measurements on these ancilla qubits, because these are the ones which we control when we are initializing the state of the systems. So there's a system register, there's a phase register, and then finally, there is something which we will call one ancilla qubit, just one qubit, bit which is then initialized in, sorry, not in 0, but initialized as 0. So what does that mean? The whole system is then given by a state which we call psi0. And psi0 is now given by an subscript A for ancilla qubit. Then there is a phase register, and when we put the subscript P, and then we have the state B with a subscript S for system. So these are the 3 different registers which we have. So in every case here, there are tensor products, okay? But I will suppress this tensor product notation. So this is the way we initialize the system. So think back to everything you've been doing. If you think of the VQE, which you had in project 1, we initialized the system as a tensor product of qubit 0. And that was our initial states. And then we performed rotations, we had control NOT gates, we entangled the system, and then we optimized the parameters of the rotations. So we can write this in full glory as 0 of A, of 0, of P, tensor product here. I'm gonna skip the tensor product notation between these different states, just of plain laziness, or in order to reduce notational clutter. By linearity, the algorithm which we are going to develop can be analyzed on each component uj. So each of these components here, the way we're going to set up the algorithm, can then be analyzed separately. So why do we use the QPE? So that's an intermediate question which we should ask. Why the QPE? Now, one of the reasons is actually pretty simple, is that the inverse of A is not unitary, given by a unitary matrix, is not unitary. So this is a basic assumption, because the only assumption we made is that H is emission and non-singular. That does not mean that it is a unitary one. So that means that we cannot apply it directly as a quantum gate. That's an important aspect. So what we do then is that we define the unitary transformation, and I'm suppressing t as a variable of e of I times a times t. So this is my unitary transformation. And you will now quickly see the link with the quantum phase estimation algorithm. So if we do that, what we have then, so let's just wait till everybody has had time to write down everything. If we do that, then when we know that we have defined A to have eigenstates U of j and eigenvalues lambda of j, that means that if I act with U on U of j, this is going to be the same as E of lambda j times T multiplied with U of j. And if we then compare with phase estimation, comparing with the QPA, when I say phase estimation, it's obviously always the quantum phase estimation algorithm. So sorry, this should be if I take U acting on U of j. This is something which we then can rewrite as 2 pi I of phi j multiplied with U of j. And this relation is what we discussed last week. I gave you a kind of a digression where we show that this expression is correct. And this is the same as lambda j times t divided by 2 pi. So the QPE converts the eigenvalue information into a register that can later control operations. So let's just write this down. So the QPE converts the eigenvalue information info into a register, and that is what we call the phase register. So this is where we have the QPE element into a register that can later control operations. So what happens when we do the QPE? So when we do the QPE on this specific state, the thing which is special then is that we can actually get this information about the eigenvalues. So when we do the phase estimation, the QPE part, what we have is that this original state, so if you remember back to what we did in the beginning, so U of j is the state we are searching. This is then given by lambda j, where we recovered information about the phases in a bit representation, and then tensor product with U of j. So if you remember back to the quantum phase estimation algorithm, what we did then through these different Hadamard and the controlled U operations, so I'm not repeating everything now, is simply that we now can recover this encoded information about the phases. So lambda j tilde, that is the binary approximation to the eigenvalue. It's a binary approx to the eigenvalue. So that means that by linearity then, what we have, by linearity, we get a new state, psi1. So we have performed now the quantum phase part. So we have the original 1A, which is unperturbed. And then we have a sum over j. We have the beta j. We have the register information, the phase register information, which is now being altered. So I'm putting a P here, that's the phase register. And then I have my system state. This is the one I'm searching after. And each eigenvector u of j, which we have here, if you look at these eigenvectors, is now entangled with its corresponding eigenvalue register. So these two guys here are now through the operations which we have done, they are now entangled. So let me just quickly remind you of that by looking back at the slides which we had. So let me just do that one. Share the screen so that we have everything clear here. Let me find the right one. Here we are. So let me just quickly remind you of what we are doing. So this is the part which we have done. So we have obtained these states. And that means that we have essentially performed the phase estimation circuit. So this is the vector u, which we call the system. And these are the phase registers with a given number of qubits. And we have performed this operation here, but we are not. And then we have extracted the information about the phases. And that means that we are here. So that maps it to that specific state. Okay? So let's just leave that one and then go back to the whiteboard. So we have a new state, which is now given by this psi1. And now what we want now, if you think back to what we wanted. So in here, we have now the information about the eigenvalues. These are the eigenvectors which we are looking after, or the solution to the problem. But we haven't said anything about this one. So what we would like to now is to have an ancilla part, and this is where the ancilla comes in. So we want an ancilla amplitude which is proportional to 1 over lambda j. So this is basically what we want now. Because if we have that, remember that what we want is actually j times beta j divided by lambda j times u of j. This is the solution we are aiming at. So somewhere here, we would like now to plug in this information. So what we're going to define now is a constant. This is just a technicality which is used in order to set up the right superposition. So in a principle, what we are going to do is a kind of Hadamard operation on this ancilla qubit. So let's now look at what we could do. So we just choose a constant. And this constant is then given by C. So we choose a constant C so that C divided by lambda j is less than equal to 1 for all j. And then what we are going to do now is to make a controlled rotation. So this is the next thing which we do now on the ancilla qubit. So what it means then, if we now look at the state which we have, so if we look back here, we have this lambda j. So that means that if we just take that element, lambda j tilde, tensor product with A, this is going to change into a lambda j. And now we have performed this rotation. So we get 1. So this is just a normalized state of C of lambda j squared times 0 plus, and then so if you take the state which you have here and you require that it's normalized, you will see that this state is the new state. The one which we have here is actually a normalized state. and C is just a constant. Now, what we then get, and now we're going to take a break, but I just wanted to write down. So the entire superposition then becomes equal to is then equal to the following. So I get a new state, psi 2, and I regroup according to the ancilla state. It's going to be given by 0 of A. I have a sum over J, a beta J, and I have this 1 minus C squared of lambda J squared. This is multiplied with lambda J tilde, the QPE change state of U of J, plus 1, and this is the ancilla qubit in a superposition now, EJ C of lambda J tilde of U of J. Now, there is an undesired element here, and the undesired element is this one. So what we are going to do now is that we are going to actually, when we now look at this specific state here, we are going to make a projection where we get rid of the state 0, and we only left with the state 1, and then we have something which looks like as we want to do. But we need some additional operations, and the additional operation is actually to apply an inverse QPE on this state. And this is something which we'll do after the break, because then we will have reached the final state which we are interested in. Because this is not the final stage, so we're actually going to perform and apply the inverse QPE on this state here. And when we apply the inverse QPE, we are still going to keep this linear superposition, but then we will make the measurement on the state 1, and then we will get something which actually is close to what we want at the end. So let's take a small break. I went a little bit over time, but let's take a small break here, because we are almost done with the basic mathematics of the HHL algorithm. So where we were before the break was that we now had performed a controlled rotation on the ancilla qubit, and now we have an entire superposition which contains the ancilla system with a subscript A, and then we have the phase register where we have put a subscript P, and then we have the system which is the U of J. So if we just stick to these subscripts which we have, which define the registers which we have. Right. So the inverse QPE now is given by the following equation. So we apply, then the next step is to apply an inverse QPE. And we do that on the state lambda J, which when we do this, we get a new state, which we are going to call for psi of 3. So let's set that one up. Because when we have this state, we are going to project out the state 1 of the ancilla qubit. So we're going to perform a measurement on the ancilla qubit. And the outcome then is going to be simply a state, which is the desired state. So let's now do that. So we will get, after the inverse QPE, we get this psi of 3 here, which is now a total superposition of the following states. So we will have back 0 of O of M. So this is the state back. So this is the inverse QPE. And when we have that, this is multiplied with a sum over J. And then I have my beta J and 1 minus C squared of lambda J squared multiplied with U of J plus this ancilla qubit, which is in a linear superposition now of 0, and this is the tensor product of these states, and I have J of beta J of C of lambda J of U of J. Then we are now going to make a measurement. So measuring on the ancilla qubits, measuring on the ancilla qubits, and where we project out the state 1, then the remaining system state is given now by, so projecting out 1A, that gives us a state now which is equal to x tilde, equal to this constant C, and then I have a sum over J of beta J, lambda J, which I have extracted from the quantum phase estimation, multiplied with the state U of J. This is nothing but the state which we want, but with a constant C, which we can then define by normalization. So this is essentially what we are looking after when we now want to solve the equations. So this state, x tilde, is a state which we can normalize. So after normalization, what we are going to get then is the following. So let me just put this down. So after normalization, what we get then is the desired state. So this is given by A inverse multiplied with this vector B divided by the norm here, A minus 1 times B. So this is just the norm 2. And this is the final answer. And this is actually what we want. So in this specific way, we can actually now solve a linear problem, but where the vectors are encoded as quantum states. Then obviously, if you want to go back to the classical representation, you would have to decode the data because B is often given by some classical data. So what I'm going to do now is to, after this excursion on the whiteboard, I'm going to go back a little bit to slides, and I'm going to show you an example, an impressive example of a 2x2 matrix, which then illustrates the basic steps which we went through on the whiteboard here. But let me try to summarize many of these steps by going back to the slides which we have for this week. And then at the end, we are going to look at how we can program this. And there are some two code examples, one which simply solves the linear algebra problem. So if you look at the original problem which we had, what we wanted to is to solve this problem where we now have not specified anything, but what we are solving is actually this problem here, where B could be some classical data, it could be quantum data. If it's a classical data, they are transformed into a quantum representation, and B and X are quantum states. So with this recipe, we have now the possibility where we use the QPE to actually find the solution to this linear algebra problem. So let's go back to the slides and summarize a little bit of what we have been talking about now. So let's just go back to the weekly slides. So the main idea, as we have exposed through the whiteboard, is actually we want these eigenvalues. These are going to be the coefficients in front of this linear expansion in the solution. We know that A, the matrix, is not unitary, so we proceed indirectly. We perform a phase estimation of this quantity. We store this information in the phase register, and then we perform a controlled rotation whose amplitude depends on this one. We uncompute the phase register, and then we post-select on a successful ancilla measurement. So we make the measurement on the ancilla qubit. So this is the system, the way we set it up. So we have the system represented by a state B. This is the known vector. We have an initial state, which is given by all the qubits in 0, and we have m qubits, and this is the quantum phase estimation part of this unitary operator. Then we have the ancilla qubit, and after we did that, we have now a rotation on this vector 0, and this qubit 0, and that gives us a linear superposition in terms of qubit 0 and qubit 1 for the ancilla system. Then what we do next is that we perform a inverse QPE in order to get, obviously, the inverse eigenvalues. And when we have that, we have a linear superposition, which is, I'm going to show you the equations again, so I'm going to repeat a little bit. And then we make a measurement on this qubit. And with that measurement, we extract information about X, which is then proportional to the inverse of A times B. And this is essentially what you will find in the slides here is just a repeat of what we did on the whiteboard. So everything we did on the whiteboard is also in the slides. So I'm not going to repeat these ones because you have it in the slides. And typically the success probability is a norm squared of the ancilla 1 branch, which we looked at. And this is essentially the norm squared which we're looking at. So this is basically the circuit. So we have the 3 blocks this is a spectral decomposition. And then we have the inverse weighting through amplitudes. And then we have the spectral recombination here. So these are the 3 blocks which enter the HHL algorithm. So the way you can look at it is an algorithm which then has the QPE as a basic building block. And the QPE has a quantum Fourier transformation as a basic building block. So you can think of the QFT as kitchen item 1, the QPE as the next kitchen item. And when you have a code for these parts, then you can use that in Shor's algorithm. You can use it for the HHL algorithm, etc., etc. So QPE, quantum phase estimation, is a very important ingredient. So as I said, the first step, and these are all tensor products which we have suppressed here. So you have the QPE block, and this is the green block here, this one. Then after the green block, this is your new state. This is the moment where the hidden spectral decomposition of B becomes explicit. Then the blue block, which is this one, it's supposed to be blue. I'm pretty bad with colors, actually. I'm really bad with colors. I have problems with some colors, like pink. I always make a mess. And the blue block acts conditionally on the eigenvalue register. So this is the eigenvalue register linked with the ancilla qubit. And then we get this rotation here, where we have a state which is a linear for the ancilla, which is a linear superposition with 0 and 1. And the full state becomes this one. And the inverse weights are now encoded in ancilla qubits. And then the inverse green block moves the eigenvalue label. So that is the next green block, inverse QPE. And that finds the new state. And this disentangles the phase register from the system. That's actually very important. And then we measure. And if the outcome is 1, then the system is left in this specific state. And then you normalize, and then you have the final HHL state. And this is essentially what is encoded in the examples, the program examples you find in the lectures. So one of the things which I put in here is a kind of simple example. So this matrix has, and you can quickly see that, has 2 eigenvalues. It has eigenvalues 2 and 4. The matrix is also Hermitian. The eigenvalues are positive. This is actually, the being positive definite is also something which is very important for the type of problems which we are solving. So when we are going to jump into Poisson's equation, the matrix we end up with is a positive definite matrix. So it's this case is just simple enough. So you could think of your source state could just be given by that one, right? So it's a 2 by 2 matrix, so we need only 1 qubit. So the source state is that B, and just suppose that one is given by qubit 0. Okay, this is just a plain example. These are the eigenpairs which we get. Lambda 1 and lambda 4 and lambda 2 is equal to 2. These are obviously the eigenvectors. And if you put them together, you can see that this is a transformation here in terms of the basis of qubit 1 and 0, which is actually given by a Hadamard. It's actually pretty neat. Right? So then these are the eigenvalues, nothing surprising here. So when we do the spectral decomposition, then we can actually set up that immediately. You can write B now in the eigenbasis. So this is a case which is perhaps too simple, but it illustrates the basic processes in the HHL algorithm. So that means that the coefficients are given by these, and therefore the inverse one is simply given by this one. And what you see is also that the small eigenvalue receives the larger inverse weight. This is also an important aspect. Then you convert back to the computational basis. So you find the inverse matrix, then you have the inverse matrix here, and then you find the final solution. So everything we did here is actually a classical calculation. There is no HHL algorithm, okay? So what I simply did here was just to take the matrix, invert it, and then find the solution. So if you want to use a QPE and the HHL, then this is what we need to do. So the first slides here, which you've seen here, this is just plain classical calculation, just linear algebra, where you find the inverse of the matrix, and then you have it, okay? This has nothing to do with the HHL algorithm. But then what we need is actually to have the QPE, which acts the way it acts in this example. So we need to perform this unitary transformation. And then we have these unitaries. And that means that if we start with the ancilla qubit, and we have a given number of qubits here, and then this is a state which we get. So this is a state B. So now I'm just plugging in what I get since I know these eigenvalues, okay? But the QPE is going to give me 4 and 2. So the QPE gives us this when we have performed it. So what these states are the qubit information contained in the register, which then contains the phases. So the phase register now distinguishes the two eigenspaces, okay? So that's the first step. So this is actually, so this guy here, which you see, this gets encoded like like the state 4 and state 2. When you have that, we choose a constant here because the largest eigenvalue is, now the smallest eigenvalue is 2. So you could choose it like 1. So now you see the transformation which I would get. So this state transforms like this, and this state transforms like that. So these are the basic operations which we do with a controlled rotation. Then the ancilla amplitudes become 1 divided by 4 and 1 divided by 2, which are precisely proportional to the eigenvalues. Now, in this specific case, we are choosing values, not the way they would come out from a program, but simply because we know the eigenvalues, okay? So in a certain sense, I'm cheating, but it shows you the steps of the QPE. So when you have that, after rotation and inverse QPE, the ancilla 1 branch is equal to this one. So when you do the post selection and you project out, every time you measure 1, then you accumulate. And then, so you do a given number of shots. And then you get this state here, which is exactly proportional to the inverse times B here. So which, if I go back and look at the calculations I did by hand, this is what I did by hand. So this simple example, hopefully, shows you, if I now go back to the computational basis, this is what you obtain. So the whole HHL evolution reproduces the exact inverse action of H on B. So if you look at this example here and go back to the general expressions, you have the basic essence of the HHL algorithm, which then uses the QPE as a kitchen ingredient, as a kitchen item. Okay? So the 2x2 makes the logic, hopefully, explicit. You diagonalize A, expand B in the eigenbases. You let the QPE, so this is 1 and 2 are the classical elements. QPE attach eigenvalue labels. You let the ancillar rotation multiply each eigensector by 1 over lambda j. You erase the labels with inverse QPE. You keep the correct branch by post-selection, which is 1, which you want. And then that is all really is. It's a controlled spectral inversion procedure. This is, if you want to give the HHL a kind of a generic wording to it, the way I like to think of it is a controlled spectral inversion procedure. So what we've seen is essentially this is the essential formula which we will cover. Now, what I want to do now is to say a little bit about the Poisson equation. Because this is, yeah. Let me just take off this, yeah.
But how is the provision C unstable?
Oh, this is something you just have to guess as a constant. No, it doesn't matter because at the end you normalize and then it just disappears. Yeah.
Okay.
The only thing you make sure is that, well, since you don't know the eigenvalues, but in this case you know the eigenvalues, you make sure that the ratio between C and the largest eigenvalue is less than 1. Because that often leads to the condition number being made efficient so that you can actually find and narrow down the region where you are looking after the eigenvalues. So but normally you would just set it up as a constant because you don't know the eigenvalues and then you just make a guess. But what I wanted to say something about is our implementation to the Poisson equation, because this is a pretty interesting case. So the kind of example which I put up in the code is actually this equation here. So how many of you have seen the Poisson equation? And how many of you have seen it in its discretized form? Okay, so some of you have seen it. So let me just make a small detour so that you can appreciate the final technical details. So that at the end, you will see that this equation which we have up here is an equation which we can convert into something which looks like this. Okay, so let's take those steps just as a small aside, and then we are going back to the, so we're going back a little bit to the whiteboard. So I can set up the equation here. And this is an equation which many of you most likely have encountered in different science courses. So let me just give you the matrix representation here. So the Poisson equation. So what we have is an equation of this type, d of u or dx equal to some function f of x. And typically what we also have is some boundary conditions. So we could now define that x, suppose we scale everything so that x is defined between 0 and 1. So that means that we have actually scaled our variables. And then we could have some boundary conditions. So Poisson's equation is actually in one dimension is actually an ordinary differential equation, but in more dimensions is actually a partial differential equation with boundary conditions only, because there is no time dependence. So the boundary conditions which you would have in this specific case in one dimension is some u of x equals 0, which we would typically write as u of x 0, which we also just rewrite as 0. So these are the standard Dirichlet boundary conditions. And then we would have u of x equal to 1, which I'm going to rewrite in terms of n, x of n. So we are discretizing, and this is u of n. We can also set that one to 0. So this could typically be a problem where you have a spring, which is fastened in both ends, and the spring just oscillates up and down, but it's fastened in both ends. That's a typical problem which you probably have encountered in different physics courses. Actually, Schrödinger's equation for a particle in a box with infinite walls is equal to this equation here in one dimension. So we will always discretize. So when you discretize, so let me just do that as a small digression here. So typically we discretize x. In principle, I should use different variables, but I will keep the same type of variable. So this is x0 plus some step size delta x multiplied with I. And I goes from 0 to 1 up to n. So we have n plus 1 so-called mesh points, so integration points, or just discretized points. And delta x is then going to be given by xn minus x0 divided by n. And that means that the domain of x variables is given by x0, x1, x2, up to an x of n here. Now, I'm going to take the liberty of just using the same symbol for the unknown quantity u. So that means that u of x is now going to be represented by u of x of I. And I will label that as a u of I. And that means also that f of x is going to be represented by these discretized values. And I label this one as f of I. Then there is a famous approximation to the second derivative, du dx, which is now approximated with a centered rule. So we use 3 points, one to the left of the center and one to the right. So that means that what we get is u of xi plus delta x plus u of xi minus delta x minus 2 times u, and now I'm going to put I here, because this is evaluated at x of I. And this is divided by delta x squared. And I'm going to write this one as u of I plus 1 step, u of I minus 1 step to the left of the center value. The center value is u of I, divided by delta x squared. And this quantity is actually equal to f of I. I'm then going to multiply away delta x squared. So I can then have u of I plus 1 plus u of I minus 1 minus 2u of I is equal to some f of I tilde, which is the same as delta x squared times f of I. Now, this is an equation where we know the endpoints. So keep in mind that the endpoints are known, so we don't need to find them. They are equal to 0 by the Dirichlet boundary conditions. So that means that the unknown vector which we have, the unknown quantity u, is just given by u1, u2, down to un minus 1. These are the unknowns. And what we can do now is actually to rewrite everything in terms of a matrix. So the problem which we had becomes A times U equal this vector F tilde. And the matrix A is given by -2 on the diagonal and 1 above and below the diagonal. So this is a 3-diagonal matrix. And the algorithm which is used is called Thomas algorithm. And it's actually another instance of what we normally call a lower and upper decomposition of a matrix. So if you use the standard algorithms, actually it's a Gaussian elimination in principle. That's what you're doing. It's nothing but that. Then you can actually show that this matrix, which is this simple, this is actually also a positive definite matrix. All the eigenvalues are positive. So this fulfills some of the desired properties of the matrix which we are looking after. So in our case, the matrix A is given by this one, and the classical algorithm, so Thomas algorithm, is the classical one. Thomas algo gives us O of n when A is now assumed to be a matrix, and in our case it's real, but we could assume that this is a complex matrix. So this matrix here gives us n floating point operations. Actually, you can do a precise count, and it's 4 times n. So we would not. So in order to find x, this is the worst thing you can do. So I'm just going to put a cross here, because to calculate inverse is actually O of n cubed operations. So you don't do that. You actually solve this by using Thomas algorithm, which is a simpler version. It's actually based on Gaussian elimination. I guess you're all familiar with that, right? So I don't need to remind you of Gaussian elimination. So you don't want to invert it, but you're actually going to use Thomas algorithm. So in the programs which you find, what I've done is actually to implement this. So there's one program which simply solves a linear algebra problem, and the other one which compares the quantum algorithm, the HHL algorithm, with Thomas algorithm. So this is what you will find in the lecture notes for this week as a Jupyter notebook. You will also find this code at the end of the lectures this week. So let's go back to the. So I hope you didn't get offended if I just reminded you of some of these basic things. So let's go back to the slides here, because I'm going to stay with the slides for the rest of the lecture here. So the example is this one, where f of x is just given by this function, and this is what we end up with. Okay, so nothing particular here. This is the problem which we end up with, which I put on the blackboard. So there is a small example here where I actually go through the n equal 2. So this is just a repeat of the other small example. So I'm not going to go through this one because it's just exactly the same exercise as we did before. So this shows you how you can actually find the eigenvalues. So I'm going to skip this one. This is basically what we looked at as a worked example for the other case. But you see now that the type of problem you have is something which you can really play around with if you can define a linear algebra problem which is of relevance for your, let's say, scientific applications or scientific studies. So if we now look at the Hamiltonian simulation here, it implements this unitary. It has a quantum phase estimation, and the HHL combines a Hamiltonian simulation, phase estimation, controlled rotation, and computation, which is inverse phase estimation, and then a post-selection. So then you make a measurement, and if the measurement gives you qubit 1, then you start accumulating. And a discretized 1D Poisson equation gives a concrete and instructive worked example. And as I said, the kind of take-home message, the HHL is best understood as a spectral filter algorithm for the inverse of A. Remember now that we have represented A by its spectral decomposition. And for differential equations, if you can discretize PDE into a sparse linear system, then the HHL produces a quantum state proportional to the numerical sum. That's pretty neat. That's one of the reasons why I like a lot this algorithm here. But what I wanted to say a little bit about, and in the slides here, there is a long digression with links to many-body physics. So this is something which we are not going to discuss in depth, because this pertains more to people who have taken a course in many-body physics. But it shows you the links between many of the standard many-body methods. Because if you think of, I don't know if everybody's familiar with the Green's function. So if you look at the Schrödinger's equation, the way you've seen it in most textbooks, it's presented as a partial differential equation. So it means that, for instance, if you take away time, you can reduce that one to sets of coupled ordinary differential equations. So that's one way to solve Schrödinger's equation. Alternatively, if you stick with time, you can solve it with partial differential equation methods. Or if you've taken a course in many-body physics, you may have encountered what's normally called full configuration interaction theory, which means that you rephrase the equation as an eigenvalue problem, where you diagonalize what's called the Hamiltonian matrix. Then you have diagonalization. So you move from solving ordinary differential equations and partial differential equations, which are normally limited by dimensionality, because if you have 3 particles in 3 dimensions plus time, then this becomes a 12-dimensional problem. And that becomes quickly intractable. And that's why you would rephrase it as an eigenvalue problem, but that is limited by the size or the dimensionality of your space. But a full diagonalization case is often a very efficient way of dealing with that. Now, you can then use approximative methods like Green's functions. The Green's function, if you want to put that on a mathematical algorithm level, it's nothing but you calculating the inverse of the Hamiltonian. So a Green's function means that you have some z here, which are actually the eigenvalues, and they define the poles of the Green's function. But you can rephrase Schrödinger's problem in terms of a Green's function. So you see the link. So if you think of this equation here and you make the link with Green's functions, then the HHL could actually be viewed as an algorithm for applying a resolvent operator to a source state. So a Green's function is in principle, mathematically, a matrix inversion problem. Now, for those of you who took a course in many-body physics, you have encountered many-body perturbation theory, which mathematically is a Taylor expansion around an energy. Then you encountered mean field methods, like Hartree-Fock theory or density functional theory, which in principle, when you look at the way you solve it mathematically, is a set of coupled nonlinear equations. The same applies to copper cluster theory, which gives you a set of coupled nonlinear equations in the unknown coefficients. So you see, the way we are solving many-body problems is actually through different mathematical algorithms. Then you can do Monte Carlo methods, or you can use neural networks. All these are classical methods. What we are doing here, however, with a quantum computing algorithm, is that we actually using a physical system to implement another physical system. So when you solve these different methods, the classical ones like full configuration interaction theory, copper cluster theory, Green's functions, etc., they reflect different mathematical algorithms for solving a problem. And historical people have always fought each other. My method is much better than your method, but they all have their pros and cons. A Green's function is ideally a very efficient method of solving problems, except that you have to face the problems of the poles of the Green's function, which are the cases when you have the eigenvalues z times I times h equal to 0. So this is just one way of viewing what we are doing. So if you look at the Green's function, if you think of the spectral form of the Green's function, this is the way you would write the resolvent, using a spectral decomposition. So why do I bring this up? If you think of what we did with the HHL algorithm, is actually to start with the spectral decomposition. So let me quickly say a little bit more, because what we did in the HHL is this. So we found this inverse here by applying the QPE, rotation, inverse QPE, and then we have this one. So this is essentially what the HHL does. But if you then look at the Green's function and the spectral decomposition, right? So these are the inverse eigenvalues for the problem. And then you can actually rewrite it. So it's structurally identical to the HHL transformations. So the HHL implements the same spectral inversion mechanism, except that the problem with the Green's functions is something you would solve on a classical computer with a given algorithm for finding the inverses of a matrix. Here, we are using a physical system to solve the equation. That's a big, big difference. But you can think of this as kind of general methods which have lots of similarities. So this factor here is something you can think of as a spectral filter, and the eigenmodes with energies near zero are enhanced, and eigenmodes far from zero are actually suppressed. And the inverse operator encodes propagation and response properties. So in this sense, the HHL algorithm is not merely a linear solver, it is a spectral transformation algorithm. That's the way I like to look at it. So that's my own, how to say, bias here. It maps a source state to a response state through an inverse operator. And then you can play around. So yeah, I'm going to skip some of these things here because this becomes more specific for those of you who have taken a course in many-body physics. But I also wanted, so at the conceptual level, it performs three tasks. You decompose the source state into eigenmodes, you invert the spectral coefficients, and you recombine the filtered eigenmodes into the response state. And this is essentially what a Green's function method is doing as well. But these are typically encountered, these methods are typically encountered when you take a course in many-body physics. But the Green's function is something which also appears when you're solving differential equations, right? You know that the diffusion equation has a Green's function as its solution. So this is a kind of, I promised you a set of digressions. I wanted to also bring up, so this is just a little bit technicality. There is also a method which is called time-dependent Hartree-Fock, which some of you have encountered, and that describes the evolution of a mean field through a Slater determinant on the time-dependent mean field. And then you can set up this as at a one-body level, and you're studying the solutions around a stationary problem, and that leads to an equation of motion for the fluctuation delta rho. And this is something which you can actually rewrite in terms of after linearization, in terms of a matrix equation of this form here, where this L is a linearized Liouvillean, that's called in a random phase matrix, and S of t is an external driving force. In the frequency domain, this becomes actually equal to a matrix inversion problem. So you see immediately that this equation here is essentially the algebraic structure which is addressed by the HHL algorithm. So there's so many interesting similarities here. And in the lecture notes, what you have is a lot of links here where you can actually set up time-dependent Hartree-Fock theory as a kind of HHL type problem. So I'm going to skip some of this because there's a lot of blah, blah here, which links with the many-body physics. And we already repeated this. What I wanted to say, so let me skip some of these things because these are just connection to many-body physics and it's not so important. So the kind of conceptual value is that you have a QPE spectral inversion plus state reconstruction, and you can actually look at that as a quantum inverse operator method. That's the way I like to look at it. So we have some codes, and I see my time is running out. So I was hoping also to start with a QAOA algorithm. But what I will do next week, and by the way, next week, the lecture will be a recording because I will be away for a workshop. So I will record the lecture and you will find the notes on the quantum approximation optimization algorithm. And I will also discuss the codes here. But you have the codes in the Jupyter notebook as well. So the first code actually writes, so everything is spelled out in a simple, very simple problem. It just solves the linear algebra problem. And again, I hope you don't get offended because I just got 2 by 2 matrix because I can do everything by hand and then I can follow the code and check that it's giving the right result. So what the first code is doing, there is a, in the Jupyter notebook, you will find everything. So it has a register layout with 5 qubits, and it has a 1 ancilla, and then there is the system, and we have 3 qubits. M is M, which we had in the phase register. So we have in total, we have something like 5 qubits. So the Hilbert space dimension is actually 32 here. And there is a code structure. So maybe I should rather actually go to the Jupyter notebook here. Let me just stop that one and go to the Jupyter notebook. I have to find my, where did I put it here? Here we are. So in today's week, in the lectures, what you will find, so this is, you will find the same codes in this file here, which is described, it gives more descriptions. And the Jupyter notebook is the one we are viewing now. And the first case is actually solving just a plain linear algebra problem. And this is the linear algebra problem. And it contains a problem setup, the qubit registers, the state preparation, the quantum phase estimation, which we also discussed last week with the inverse QFT. Then it has the controlled rotation, and then it has the inverse QPE, and then there's a post-selection here. And then it selects the solution and compares with the classical result. So this is essentially what you will find in the first code. And you will find everything, basically, I actually had a bug here when I was looking at it. By the way, if you haven't used this before, softwares like Gemini, Claude, etc., please use them. So I had a bug in the original version, and then I just grinded it through Claude code, and it found the bug immediately. So when I set up my structure, I actually had a pretty stupid bug where actually I was mapping things wrongly, and you can see the summary here. So bugs fixed in this version, actually. There may be more bugs, but I hope not. It actually gives the same results as the classical case. So I actually wasted last weekend finding that bug before I said, okay, let me see if Claude can help me. And it took just a few seconds. That's when you feel stupid. So this is the code here. And if you scroll down to the next case, so the final case, so this is just basically doing everything. So if you want to encode this and study it, I mean, please use this as an example, and you can see the calculations and the comparison with the classical one, and you're basically getting the correct results. I'm just skimming quickly through it because the next case is actually solving Poisson's equation. And this contains the standard finite discretization. I have included Thomas algorithm and a grid convergence study. Actually, this is, it's very hard for the quantum algorithm to beat Thomas algorithm. And then it contains the HHL block, which is based on the previous program. So essentially what you see in these programs is what we went through in the lectures, but just encoded with a quantum phase transformation, quantum Fourier transformation, and inverse QPE and rotations. And that's it. So next week, I'm going to pick up a little bit here because there are some interesting links with quantum machine learning. But then I'm going to focus on the quantum approximation optimization algorithm, because that gives us a very nice link with quantum machine learning and the general concepts of parameterized quantum circuits, which you encountered with the VQE. So these are all algorithms which apply to this noisy intermediate state quantum computers. So you will see that they are going to be hybrids where we set up the basic algorithm, which runs on a quantum computer, but the gradient part and the optimization part is solved on a classical computer. The gradients are actually computed on a classical computer. So this kind of hybrid approach, which you employed in the VQE, is something which you will see with the QAOA and also in all the quantum machine learning algorithms. The QPE, ideally, is a pure quantum algorithm, but it gives very long circuits. And then decoherence times, noise, etc., start playing a major role. And that's why we end up with this kind of hybrid algorithms. So the optimization part, which you will see next week, is always something which will be treated classically, the gradient part. Here, the HHL is a pure quantum algorithm. But next week, we come back to parameterized quantum circuits or variational quantum circuits, which is a more general container for many of the things we are doing. Does that sound okay? So next week, the lecture will be recorded, but we will have exercises anyway, if you want to discuss projects, etc. Okay? Okay, we stop here. Huh?